like we always do. What did we last class? What did we start with? Right. So we simply said standard inner product is just another form of matrix multiplication. Okay. And then what is an outer product? Yeah. What is an outer product? So if you have two vectors Rn, yeah.
Right.
Oh, okay. Y transpose, is it? Okay. And what is this? Where does this belong to? The outcome? R? Yes. Is it from Rn? Okay. And if the inner product was row times column, this is column pressure. All right. And then see in the inner product, both x and y, x transpose and y. So x comma y had to be from Rn. Do we have the same restriction here? Then x be from Rn. Rn. Is it possible? Sorry.
The one that should factor its low should be equal to the minus one.
Okay, I'm asking you if it's satisfied. That is what the question is. So you can take the outer product between these two vectors. Yes. By doing this, because this would be of size n cross 1. This would be of size n cross 1 cross n. So it does match, right? What will the outcome be though? Where will this belong? What will this belong to? You can have outer products between two vectors from two different spaces. Not just in Rn, they can be from Rn and Rm. Okay. And then yes, 4 interpretations of matrix multiplication. So what are the 4 interpretations? The inner product interpretation. According to that, if C equals AB, what is Cij? The ijth element. How do you get the ijth element of the matrix resulting from multiplying A and B? You have to be louder. You take the ith row of A, which is represented like this. You take the jth column of B, and you take their inner product, and that will give you this. Okay. Then, what is the second interpretation? What is this? According to this interpretation, how do we view matrix multiplication? Right. The ith column of C. No, the column interpretation, right? Okay. Okay, so we can write this linear combination of what? Oh no, A is a matrix. Column interpretation. So the ith column of C is the linear combination of what? No, yeah, what do you mean by linear combination of a matrix A? Linear combination of matrices would be something like this. No? See, again, this is something you should know by now. So if you have AB, the ith column of C is what? Is a linear combination of the columns of A with the sorry yes with the mixture coming from the B. So all this to say CI is nothing but A times BI. That's all. Okay. The I row C. You'll have to be louder. I don't hear very well. So whatever you say, please be louder. Okay. I row. Okay. You take the. Okay, no. It cannot be the linear combination of the ith row of A, right? It is the linear combination of what? The rows of B and the mixture comes from the ith row of A. So which you can write as, because if you pre-multiply a matrix by a row vector, you're taking the linear combination of the rows of the, sorry, if you pre-multiply a matrix by a row vector, you're taking the linear combination of the rows of the matrix, and the mixture for the linear combination comes from the elements of the row vector. Okay? This also means if you only want to know a specific column or row of this matrix C, you don't have to do the entire matrix multiplication. You only have to, in fact, you don't even, if you want to know the ith column of C, you only have to know the ith column of B. If you want to know the ith row of C, you only have to know the ith row of A, but the other matrix. And the last one. Product. What is this interpretation? Ith row of A. C is what? The sum of B outer products. What are those B outer products? Again, B outer products, because I'm assuming this is from R cross B and this is from B cross R. That's assuming. Outer products of what? There are P outer products. That means I'm multiplying P columns with P rows. You take the ith column A, the ith row B, add them over. These are the individual outer products. There will be P outer products because A has B columns, B has P rows. If you take the corresponding ith column of A, ith row of B, you take their outer product and you add them all together, you will again get C matrix. See, as I said before, when I say it standing there, it all seems very natural. But when I ask you, you're not able to say. That means you have to go back and really know these things by heart. Anyway, yeah. Please spend a little bit more time going through this so that you're completely comfortable with all this. Okay. And when I ask you something very basic like this, you should be able to tell me immediately. When I say what is this ith column of C in terms of A and B, you should be able to tell me this immediately. Okay. And then what did we talk about? Yeah, okay. We looked at some properties of matrix multiplication. And then yes, yeah. What is the linear transformation? It's a map from. Okay. And when is it linear? Yeah, if it satisfies the superposition. position. And what is the connection of linear transformation with matrices? If f is the linear transformation from Rn to Rn, how is it related to the idea of a matrix? Yeah. What do you mean by n cross n? So this linear transformation f is determined or is represented by a matrix that is of size n cross n. That's all. That means we can think of matrices as representing linear transformations. Okay. Rn space to Rn space depending on the size of the matrix. Okay. Then rank, yes. Matrix. What did we say was the rank of a matrix A? If you have A, again, Rn cross n, what is rank of A? Well, what did we define it to be? Dimension of. When you say dimension of something, you're always talking about dimension of a subspace. What subspace are you talking about? Span of what? N or n? I mean, this is also equal to what? Yes, all the rows. How many rows do we have? Okay. This subspace, what is this a subspace of? Rn or Rn? N. Because the columns come from Rn. This one? Okay, that's where we stop. Okay. All right. We continue this discussion. Again, let's see. So see, this says this is the dimension of this subspace, right? That means it's essentially the number of vectors you will have in a basis for this subspace. Right? That was the definition of the dimension of a vector space. If you have a vector space V, what is the dimension of the vector space? Again, this is something you have to know by now for sure. Because you only have to remember. There is no understanding here. How is the dimension of a vector space defined? Length of what? Yes. Yeah, exactly. So this is a vector space. That means there is a basis V for this vector space. What do I mean by a basis for the vector space? What is the basis? Right. Exactly. So basis is simply a set of vectors. It is a linearly independent set that spans V. That means every vector in this vector space V can be obtained by simply taking the linear combination of elements of V. Okay. Right. So that's basis. What is the dimension of V? Like you said, is the number of. So this hash of operator simply tells you if V is a set, hash set tells you the number of elements in the set. That is simply the dimension of V. Okay. That means here, if you go back here, if the rank is the dimension of the subspace of the columns of A, subspace formed by the span of the columns of A, it also tells me that if I have a matrix A, A1, A2, AM, right? If I take the linear combination of these, I get this. Okay. If I randomly, let's say I'm forming a set, okay? I randomly select one column and I put it here. Okay. And then I ask you, is this set linearly independent? Is this set linearly independent? When will this set be linearly independent? Set of one vector. It must not be equal to 0. If it's 0, then it's linearly independent. As long as this is not the 0 vector, you're fine. This is linearly independent. Because if it was the 0 vector, then any non-zero alpha times 0 will give me the 0 vector. That is against the definition of linear independence. But if it is a non-zero vector, if I multiply it by alpha, since this is non-zero, the only way this will be equal to 0 if alpha is 0. That's the definition for linear dependence. Okay? Okay. As long as this is not the 0 vector, you're fine. This is the linearly independent set. Okay. Now I sample it again, but I don't. Let's say I'm sampling it without replacement. I take the ith column out, and then I sample again, and then I get let's say I1. I get I2. Is this linearly independent? This set now. What is the condition for this set to be linearly independent? Set of two vectors. See, as long as these two are not collinear, then this will be linearly independent set. Okay. And again, if you simply apply this condition, what I just said, algebraically just means this. This is equal to 0 when alpha 1 and alpha 2 are equal to 0, then the set is linearly independent. As long as that condition is satisfied, this is linearly independent. Let's say I continue that, right? Now, the rank of A, you can think of it in terms of linear independence. The rank tells you the maximum number of vectors you can take from the columns of A and still form a linearly independent set. Okay? Let's do some examples, then it becomes easier. Say A is this. Okay. What is the rank of this matrix? Rank is a single number. What is the size of the matrix? Is 2 × 1? Yes, yes. Why is it 1? Let's start with here. This is the definition of the rank. Rank 1 is correct. Why is it 1? Okay. So if you look at the span of this column vector, right? It's an R2, so we can draw it. This is 1, 1. The span of this vector is, there is only one vector. That means this forms the basis for the span of A. The span of this column. There is only one vector in the basis. That means it's of dimension 1, so the rank is 1. Okay. So here, rank. Let's simply say R for now. Assume R is the rank of A. It's 1. What about this? Two. Okay, explain why is it 2? It's correct. It's 2. Why is it 2? Okay, 2 ways to look at it. Okay, what is the span of the columns of A? This vector 1, 1. What is the span of this? It's R2, right? So one vector is 1, 0. It's like this. One of the vectors is like this. This is 1, 1. This is 1, 0. They are not collinear. And you can obtain any vector in R2 from this. That means this is span of this is R2. Right? And is this, well, I can ask you what is the dimension of R2? To span R2, you need 2 vectors. So Why is not? The span of this matrix, the span of the columns of this matrix, span of the columns of this matrix are exactly the same. 1, 1 spans this. 1, 1 and 1, 2 still span the same subspace. Okay, and the dimension of this subspace is 1. So the rank of this is 1. Now let's look at this idea of the size of the maximum possible linearly independent set that you can form from the columns of A. Okay. Now we have this matrix. There is only one to sample from. The only thing I can sample from here is this 1, 1. There is nothing more to sample, so we stop here. Is this a linearly independent set? It is, right? How many elements does it have? 1, means the rank is 1. Okay. So what about here? Let's say first you first sample 1, 1, 1. And then 0. Is this linearly independent? The set, well, it is linearly independent, but you can verify it using this condition. Yeah, this you can do by yourself. So we've sampled everything that we possibly can, and this still forms a linearly independent set. So the rank of this is 2. Here, the maximum number of columns that we can sample from here is 2, right? So we sample one of these, we get 2, 2. This is linearly independent. We can sample one more. It's not, right? So that means the moment I sample a second one, I don't get a linearly independent set. That means when I sample this matrix for its columns, and I form sets of column vectors, the set stops being linearly independent after you sample one vector. That means the rank of this matrix is 1. Okay. Let's look at one more example. One, 1, 0. What is the span of the column of A? So that means the dimension has to be 2. That means the rank has to be 2. Right? That's according to this definition. What about the linear independence? The use of the linear independence argument. Agree that let's say we first sample 1, 0. Is this linearly independent? It is. If I choose any one of these, right, as my first vector, it remains linearly independent. Okay? Let's say I've chosen this, and then I choose 1, 1. Is this a linearly independent? It is. Okay. So the rank can be 2, or rank is at least 2. Okay. Now I go ahead and sample the last one. Is this a linearly independent? No, it's not. The moment I consider the third vector, I don't have linear independence, so it's over. In fact, you should have already known it from before, right? For example, the span of this is R2. If you have a vector space, if you have Rn, how many vectors can you sample from Rn and form a set so that the set is still linearly independent? What is the maximum possible number of n? That means the dimension of this is n. So this spans R2. That means the set I can form by sampling the columns of A, that will be linearly independent. The maximum possible size set is a set with 2 elements. That means that the rank is 2. Yeah. For this. What is the rank of this? Sorry? Right? So no, the rank of the matrix. One, why is it one? So, what is the span of the columns of A? It's a span of 1, 1. 0 produces nothing. This produces a line, so the rank has to be 1. But if you use a linear independence argument, let's say we initially sample, is this a linearly independent set? It's not. So, of course, it fails here, but I could have sampled the second one as my first vector. So I choose this as the first vector and I sample 0, 0. The moment you have 0, 0, the set is linearly independent. The moment you have the 0 vector. That means the maximum possible set of vectors that I can, column vectors I can choose from my matrix that still remains linearly independent is or essentially all this points to this. You have a subspace that is spanned by the columns of A. Okay? I ask you to give me a basis for this vector space using the columns of A. The question is, how many vectors will you have? Will that basis have? That is essentially this idea of sampling from the columns of the matrix and looking for a linearly independent or maximum possible linearly independent set. All you're trying to do here is you're finding a basis for the span of the columns of A, and the basis is a linearly independent set that spans the entire vector space. The entire vector space we are looking at here is the span of the columns of A. Okay. See, as we go along, what you will find is many of these ideas are all related to each other. Okay, so whenever you come across a new idea, it's good practice to try and think about it from different angles in terms of dimension of the sub, in terms of linear independence. That will help you form a more complete picture of this whole set of concepts that we'll talk about. Okay, okay with that, we will move on. Now, you can use the same set of arguments in terms of linear independence with the rows of A as well. For example, you could have done the same thing here. You ask what is so the same idea of sampling from the rows of A and then finding out what is the largest possible linearly independent set I can form. For example, if you had A, again, the first one, this is linearly independent, and then I sample another one, and then I get 1 again. This is not linearly independent. Okay, that means the maximum possible set of rows I could have chosen that was still linearly independent is 1. That means the rank of this is 1. The same applies here in all of these. If that is the case, right? If I have a matrix, rectangular matrix, n, okay, what can you say about the rank of A? Or what can you say about the bounds of rank of A? Rank of A, you're saying it's less than or equal to minimum of n comma m. Why? How?
So the back
There is one specific example, right? Can you? Okay, fine. But how do you? Can you provide a complete argument that does not depend on one specific example? Okay, maybe it's not clear what we would get. But if you talk about this in terms of forming the largest possible linearly independent set, then maybe we can argue why it has to be like this. For example, if you're talking about the columns array, what is the largest possible uh, set you can form using the columns array such that the set remains linearly independent? Well, there are n columns. That means the maximum possible set I can form is n. Okay? But that number that I get for rank should also be the largest possible set. It should also be equal to the size of the largest possible set I can form by sampling the rows of the matrix A. Right? How many rows do we have? N. Right? That means the largest possible set that I can have, either including the rows or the columns, that remains linearly independent, has the minimum of these two. Okay? Because if I have two sets, right? No. Let me just argue like this. So, if you take the row argument, and you say the rank is the maximum possible number of rows I can have, that's the independent set. N. If you talk about the columns, it has to be M. Now, the rank has to be lower than N or M, because if it was greater than N, right, you cannot sample more than N. You cannot sample more than N columns. N columns that will still be linearly independent. Okay, so your rank has to be between N and has to be lower than N and M. What about the lower end? Can it be 0? Let's ask this. When will it be 0? Right, if you simply have the 0 matrix. One example. Right? The dimension of the span of this, or the span of the columns of A, or the rows of A, is simply the 0 matrix. The dimension of the 0, the trivial subspace is 0, because you cannot sample any vector from here and get a linearly independent set. There are no vectors that you can and form a set that will be linearly independent. So this has to be of dimension 0. So there are no elements. This number of elements is 0. So the dimension is 0. Yeah. So this is something to remember. The rank is always between these two. If it's the 0 matrix, then you know the rank is 0. Yeah. Okay. Okay. All right. Now, whenever you have a matrix whose rank is equal to minimum of n comma m, okay, then we say this is a full rank matrix. That is the maximum possible rank it could have, and it attains that. Okay. This would be a full rank. Whenever it's less, when it's lower than minimum of n comma m, then we say this is rank. Definition. That means, or another way to think about this matrix that you have A, the rows of this matrix somehow carry different information. Okay? Because they don't form a linearly independent set. Or if you take all the rows, it forms a linearly independent set. When you have a linearly independent set, that means each vector carries information that is not in the other, which can be obtained through linear combination. The same applies for the columns, but there are n, for example, if n is less than n, if you have a fat matrix, then there are n columns that will form a linearly independent. Or if you have matrix like this, then your entire set of columns that you have for the matrix, they form a linearly independent set. That means they all convey slightly different information. If you have square matrix, that means the rows form a linearly independent set, all the rows, then all the columns form a linearly independent set. Okay. All right. That's all I wanted to say about rows for now. Sorry, rank for now. We now talk about idea of matrix. Before that, you remember matrix IN, identity matrix. An interesting property of this matrix is if you take a matrix A, say this is, so now let's say it's n plus n. Okay. If you multiply this matrix A by I, either post multiply or you'll always get the matrix A, right? So essentially your I matrix, when multiplied by another matrix, does not change the other matrix. Okay? So in some way, this is like 1 for the real numbers. Because if you have any number A, you multiply it by 1, you brings us to the idea of an, right? Now if you have two real numbers, A times B, that gives me 1. Okay? Then we say B is equal to 1 by A, or B equals inverse, or A equals inverse. Okay? We're talking about something similar for matrices. The idea of a matrix inverse for now, a matrix inverse is any matrix. If you have a matrix, let's only talk about square matrices for now. Okay. So you have matrix A, a square matrix. If you have a matrix B, okay, such that if you post multiply A by B, or B multiply A by B, then you get the identity matrix. Then this matrix B is called the inverse A, and this one, it's unique. There is only one B that satisfies. A is the n cross n matrix, and if there is a matrix B that satisfies this property, it's called the inverse of A. It's unique, and this is represented by A to the power minus 1. Okay. And whenever you have a matrix A that does have an inverse, then the matrix A is called non-singular. Okay. And A is, remember, A is a square matrix. That means what is the rank of A? If it is, if it's full rank,
Yeah.
if it's full rank, it's minimum of n comma m. Well, it's only n, so it has to be n. Full rank, that means the rank of A equals n. If A is rank deficient, okay, rank A is less than n, then none of this. Such a matrix is singular, has no inverse. You can talk about a generalized inverse for something, a matrix like this, but we'll talk about them later. Okay. This is for square matrices. We don't talk about inverses for rectangular matrices. It turns out, whereas in real numbers, if you have AB, right? Well, if you can take A, multiply A inverse, multiply to the right or the left, you get 1, which is true for square matrices. But it turns out, when you have rectangular matrices that are full rank, you don't have inverse like this. You either have a left inverse or a right inverse, which again we'll talk about later in the module on matrix inverses. Okay, so again some properties that are useful to remember. Again, if A is non-singular, A is full rank square matrix, then we've already seen as A inverse. So inverse A is equal to I, and inverse of the product of two matrices. Let's assume A and B both are square. Let's say both are full rank. Then the inverse of the product of these two matrices is simply the product of the inverses, but in the opposite order. Okay. In the next module, we'll see a use of A inverse is to solve a set of linear equations. Like we'll see why this represents a set of linear equations in the next module. And the solution for this is simply A inverse B. This is where it's useful. Of course, in practice, if you're using MATLAB or Python or whatever, you never compute the inverse to solve this. There are other ways to solve this, but at least algebraically, when we write it, we can write it like this. Okay, all right. That's all I wanted to say about matrices. So we'll stop here. If there are any questions, we'll discuss it. Otherwise, we will maybe do the quiz now, and then we'll look at the tutorial for matrices. Are there any questions? No? Okay, we do the quiz? Yeah. The quiz is only from vectors, so don't worry. Minutes, is it? 10 minutes, okay. Yeah. I'll chop it later. You need extra time? Okay, maybe not. Okay, you can collect it. Okay, it's time. Do you need extra time? Fine. Okay. 5 more minutes. Sorry. Okay, 1 more minute. We'll collect it. Yeah, okay. It's time. Please make sure you've written your name on the answer sheet, please. You've written your name? Yeah, okay. No number. Nevertheless, if the name is there, it's fine. See, the quiz is also an indication of if you're not able to answer some of them. The quiz is kind of where you have to be at a particular point. You have to be able to at least not be completely stumped by the question. If you see the question and you're like, this makes no sense. Understand the question, that's reasonable. If you're able to attempt or think about how do I go about solving this, even if you don't find the answer, that's good. Okay? So if you're not, if some of those questions really stump you, then it's time to go back and review the material. Okay. All right. Are there any? How many of you have started attempting the first assignment? Everybody. Okay. All right. So you're. Were there any specific issues that you guys have? Any problems? Okay. See, if you're stuck with any assignment problem, right, you should always contact the TAs or me and wait till the last moment. You can, yes. Of course, don't come and ask us what is the answer. You can come and tell us where you stuck, and then maybe we'll help you a little bit. Yeah. Okay. Yeah. Yeah. Forever. Answer sheet. Yeah, we'll take it. Yes. Okay. Okay. So we'll do a few problems in matrix multiplication. The first one, I'm not written it there, but okay. So you remember I said transpose B. Sorry, AB whole transpose is B transpose A transpose. How do we show that this is actually true based on what we know? Okay. And I'll of course show one way of proving this. The point of this whole exercise is for you to really get comfortable manipulating things that you come across, like matrices and all that. Okay. Okay. So let's talk about A, B, right? There are different ways to view AB. What are the four views? Four interpretations. You have to be louder. As I said, I don't hear very well, so you have to be louder. Okay. All right. So the question is, we have to show something like this. There are these four ways that we can view a matrix multiplication. We can think about, okay, see, of course, you can start with this first definition. What is the very first definition of matrix multiplication? The ith element of a matrix like this. I, K, B, K, J, and K goes from 1 to, if A is from N cross P, this is from P cross M. You can use this and then try to show. You can show. Okay. We'll take a slightly, we'll take a different approach, which maybe gives you a slightly easier proof. Now, so we have to show this gives you an N cross M matrix. Okay. Now, if you take the transpose, it'll give you M cross N. We need to show that this is equal. We need to show when we say two matrices are equal, their size is equal, and each individual element match. Okay, that's what we mean by these two matrices being equal. It means we need to show that each of these elements from this matrix is equal to each of these elements. Okay. Let's see how we can do this. And since you have to show each of these elements is equal to this, one way to maybe one easy way to look at this is to compute each element for this matrix and this matrix, and then show that they are in fact equal to each other. As I said, there are these four views. Which of these four views allows you to compute each of the individual element of that matrix? The column allows you to compute the column of C. The row view allows you to compute the rows of C. Outer product gives you something weird. Inner product gives you what? The way of computing the ijth element of the matrix. Right? Okay. Now let's say I have the matrix AB. What is the ijth element of this matrix? How do I compute the ijth element of this matrix? The inner product view. Inner product of what? No, ith element. What do you mean by ith element? And? Okay. But this is for AB. What about AB transpose? Well, the transpose is holding. Now, this is a scalar, right? That means if this is a scalar, we know inner product is commutative. That means if x transpose y equals y transpose x. Since this is a scalar, we get this. Okay. What about this? What about the ijth element of this matrix? Hold on. Is my argument correct? Hold on. So now I'll leave it like this. Equals A I E chain. What about the ijth element of this? Let's leave it there for now. Now the inner product view, that means the ijth element would be the ith row of this B. What is the ith row of B? Not B, B transpose. Yes, okay. So, okay. What is the ith row of B transpose? It's the ith column of B, right? Okay. The transpose. Right. Okay, here. If I have a block matrix A, okay, that's written like this: A1, A2, A. No. Okay. This is a block matrix. What is the transpose of a block matrix? Sorry? This is the column. What about the individual elements? Is it simply this? No, you remember the transpose of a block matrix? If you have a block matrix A, B, C, D, transpose of this is what? A, C, B, D. But you have to take the transpose of the individual elements. See? The same thing applies here. That means the ith row of A transpose is the transpose of the ith column of A. See, the second row of A transpose is the transpose of the second column of A. That means the ith row of B transpose is the transpose of the ith column of B. Yes? Okay, all right. So, This is the inner product of the ith row of B transpose and the jth column of A transpose. What is the jth column of A transpose? Now let's, if A can be written like this, what is A transpose? So it will be a row. Usual element. It will simply be A1 tilde transpose transpose. Double transpose is it takes you to the original element. So it's A-N. Is that clear? So what would be the jth column of A transpose? It will simply be the transpose of the jth row of A. Okay. Okay. Now we have AB IJ. Okay. If you have a matrix A, okay, and let's say its ijth element is Aij. A. So this means the ijth element of the matrix A, that's Aij. What is the ijth element of A transpose? Not Aij. It will be the jith element of A. Okay. Question here. Okay. This is A12. This is what is A11, A21, A12. Okay. What is the ij or the okay. What is the element in the first row and the second column of A transpose? It's not zero, right? It is a zero. So it's right. It's AJI. Is it clear? It should be 9. Okay. What is AJI? Oh, not okay. What is the A? That means AB. IJ is AB. JI. Okay? The ij element of AB transpose is the JI element of AB. What is the JI element of AB? So it's the inner product between the ith row of A, sorry, the jth row of A and the ith column of B. So it's AJ transpose, jth row of A and the ith column of B. Okay. Now compare these two. This is an inner product. Inner product is commutative. At least in Rn, if x transpose y equals y transpose x. If this is y, x transpose y transpose x. That means these two are the same. And this is a general argument. That means this is in fact true. Okay? AB transpose is the A transpose. Yeah? Is that clear? No. Now, it's also true that if you have, instead of just two matrices, if you multiplied n matrices like this, then you take the transpose. This is equal to we know that it's true for two matrices. A1, A2 transpose is A2 transpose A1 transpose. The question is this also true? We don't know this is true, but how do you show that? So to show this, we'll again use some of the properties of matrix multiplication and show that this is in fact correct. See, we know this is true, right? We know A1, A2 transpose is A2 transpose, A1 transpose. That's what we've shown here. Right? Now, your question is, what about A1, A2, A3 transpose? Well, one way to understand this is, you have two matrices here. If you multiply these two, let's say you get a matrix C, right? So that means I can write it as C times A. Well, and we call it B. Right? Now, this is in the form like this. Product of two matrices and its, product of two matrices and its transpose. That means this is equal to applying here. So what is B? What is B? B is nothing but A1, A2 full transpose. So I know what is A1, A2 full transpose is. It is A2 transpose A1 transpose. Okay. So we know that it's true for 3 also. Now the question is it true for any n? It feels like it is, but one way to show right? Induction is very simple. Okay. We know that this is true for the case where n is 2. Okay. Now, if we assume that this statement is true for, let's say, n minus 1 matrix multiplications. Okay. And if we can show that if something is true for n minus 1 case, and it's true for the case n, then it shows that it's true for all cases. Now, let's assume that A1, A2 to A, n minus 1 transpose is in fact equal to minus 1 transpose. Let's assume this is true, okay, without any proof. Okay. Now, what about this A1, A2, An minus 1, An? Okay. Now, this whole thing can be combined into one matrix. Let's say B. That means it is equal to BAN transpose. We know what the transpose of something like this is. This is AN transpose B transpose. You know what is B transpose? Because we've assumed that this is equal to this, right? That means this is equal to so if something is n minus 1, it is also true for the nth case. That means it's true for all n. So no matter what n you choose here, this always holds. Okay. See, the point of this whole thing is to try and get comfortable with dealing with matrices and their different properties and how to manipulate them. Yeah. Yeah. Let's think about this here. You know, let's to me later. Yeah. Okay. Look at another problem. So there is, let's say, you have a square matrix. Okay. There is something called the trace of a matrix, trace of a square matrix, and that is simply the sum of diagonal elements of A. And don't worry about what this means. It turns out this particular entity has some use. Okay, it's simply I. Now, if you have two matrices A and B, that gives you a square matrix n cross n. It turns out the place of AB is how do you show something like this? Well, okay. Let's look at the problem. Break down the problem, right? We're dealing with the trace of a matrix. Okay? Trace only depends on the diagonal elements of this matrix. How do I compute the diagonal? Sorry?
Then I will be.
What do you mean? See, okay, you have this matrix AB. Trace of AB only depends on the diagonal elements of AB. That means these elements. The trace of AB right? AB is an n cross n matrix. The sum of the diagonal elements of AB will give you the trace of AB. Okay. How do you compute the diagonal element of this matrix AB? The product of these two matrices.
So,
Yes.
if I like sometimes not equal to I equal to J, let's say, or I equal let's say,
It is.
I
The reason I have written II is because I and J are. Yeah. So, okay. We know AB IJ is what? Inner product of ith row of A. But if I'm talking about II, what am I talking about?
let's say we have element A2 1. Two I is different. First I two is different for the element and one A is I equal to J. One will be one. Two will be two. But I will be equal to three.
Yes. So AB will simply be the inner product of the ith row of A and ith column of B.
Right.
Yes. See, all I've done is substitute J equals I.
And then you double try.
Yes. So for the diagonal elements, I and J are the same. So it's simply the inner product of AI.
Ith row taking the transpose of that eighth element of I
Not eighth element. What do you mean?
ith element of A.
Okay. There is no ith element, right? The matrix has ijth element. No? Is this clear? No.
Transpose not.
Okay. Okay. That's simply the sum of these elements. Okay. Now, we're talking about trace of AB and trace of BA. That means both these matrix multiplications are possible. That means A comma B, I should have said this before, but a square matrix. Now, can you tell me what will be the trace of BA using the same argument? Well, it's simply the sum of the diagonal elements of BA. That means BA, II. What is the ith diagonal element of BA, the matrix BA?
Eighth element. Ith row.
Yes. So BA, II is the inner product between ith row of B, ith column of A. Right? So this is B, I. Okay. Well, this does not help because these two are definitely not. It does not look like these two are equal. Now, if you expand each of these in turn is a summation, right? Inner product is a summation of the product of the individual elements. If you expand both of these, you will find that the double summation is in fact all the elements that are there here will be there here, and that is why they are equal. Yeah. So I will leave it here for you to work up. So you will have to express this as a summation again, and express this as a summation again, and you will find that within the double summation, all the terms that are equal on both of these. That means the summation, the sum of all this should also be equal to each other. Okay. I wanted to do all of them, but it's fine. We are running out of time, so I will only do a. We'll do the fifth problem, which is actually something that's very useful in practice, which is basically called the matrix inversion lemma. Let's say you have a matrix A, and that's a square matrix. And let's say it's invertible. That means A inverse exists. That is an inverse. Okay. And let's say we consider two vectors, U and V, which are from Rn. And the only condition that that these have to satisfy is these are not zero. None of these can be zero. Okay. And again, there is some weird condition like this. And this will not be equal to minus. So don't worry about this. Okay. Here is just some special conditions that these things have to satisfy. Now it turns out when you have stuff like this, let's say I have matrix A, and I add a new matrix to this form. Okay. Now I get a new matrix. It turns out you can ask, okay, I know the inverse of A is A inverse. If we take A and slightly perturb this matrix or change this matrix using this new matrix, you get a new matrix. The question is, what is the inverse of this? Okay. It turns out there is a simple expression, or relatively simple, or a nice analytical expression for the inverse of the matrix like this, which is simply given by that. Okay. And your goal here is to simply show that this is in fact the inverse of the thing on the right hand side is simply the inverse of this. That means if I take this expression and I multiply it by A plus UV transpose, either on the right or on the left, I should get I. Okay, that is the goal. You don't have to worry about what this means and all that. You simply have to show that if you multiply by A plus UV transpose on the left or the right, you do get. Again, the goal here is for you to get comfortable with manipulating matrices and vectors. Okay. I'll write down the expression here. So this is A inverse minus A inverse U P transpose A inverse 1 plus U no V transpose A. Okay. Now before we proceed, we'll just make sure this is an n cross n matrix. What is the size of this? Is this allowed? What is the size of this? UV transpose. That's an outer product, right? Both U and V are from Rn. So what will be the size of this matrix? N cross n. So you can add two n cross n matrices. It's a square matrix. And it turns out if it satisfies these conditions, the inverse does exist. Okay. That means the inverse this should also be a n cross n matrix. Right? Okay. This is n cross n. What about this? Does this still form an n cross n matrix? Okay, we look at the individual elements first. What about this? What is the size of this? It's V transpose multiplied by A inverse and U. Can you tell me what is the size of this? How do you compute? So, what do you have? You have V transpose A inverse U. Tell me what is the size of this? 1 cross 1? Why is it 1 cross 1? This is 1 cross n. This is n cross n. This is 1 cross n. Sorry. That's 1. Yeah. So these two cancel out, you get n cross 1. These two cancel out, you get 1. So this is a scalar. So you're simply adding 1 plus some scalar and you're dividing it, dividing something on the top by this scalar. So this is okay. What about the size of this? See, whenever you see expressions like this, it's good to do the sanity check and see that everything is in place. This is n cross n, okay? Because this is n cross n, this is n cross n, this thing in the middle, this thing together is n cross n. So this whole thing is n cross n. So n cross n and some n cross n matrix. So subtraction is allowed. So this is it looks all right, at least in terms of the size of the matrix. Okay. So all we have to show, if you take A inverse, A inverse U V transpose A inverse V U, and if I'll only do the when I multiply post multiply this by A plus U V transpose, you can check for the pre-multiplying as well. A plus. So if I multiply this, if this is in fact the inverse of this should come out to be IN. Okay. Now, because there are these 4 terms, we'll first multiply this by A and then derive what that is. So if I multiply this by A, what do I get? I get A inverse A minus A inverse U V transpose A inverse divided by some scalar. U transpose A inverse. We're out of time. Let's finish this. Will probably 5 minutes. Multiplied by A. So this is just a scalar. That means I can take this directly to the numerator, right? Or maybe I'll write it slightly differently if that is confusing. So I'll take this scalar out. So this is simply 1 plus V transpose A. This is scalar. Okay. Multiplied by A inverse U V transpose A inverse. And I'm multiplying from this side. I'm post multiplying by A. So A comes here. Now let's see if we can simplify this. What about this? What will this give me? This will give me I. What about this? What will this simplify to? Well, we don't know what these are, but here A inverse multiplied by A. So if I group these two together like this, right? What is this? This is I. So this disappears. So I get 1 by 1 plus V transpose A inverse U. A inverse U V transpose I. That's gone. Okay. Now we have something in the numerator here. Let's multiply it out with I. Now, if you multiply this with this, right, what you get here will be a matrix. Okay. Because if I have a matrix A and I do 1 by 5 times B, this is equal to 5 times A plus B divided by 5. Okay. So I take this scalar multiplied by I. That means I'll get some alpha times I. This scalar multiplied by I. Okay. Now, because I'm multiplying the denominator, I'll not write this again. I'll simply call it denominator. Just multiplied by I. So if I have I and I multiply it by some scalar like this, what I get is alpha times I plus like it's two matrices, sum of two matrices like that. So this will be 1 times I, this I, and then this scalar multiplied by I. So that will be V transpose inverse U multiplied by I minus this term. Okay. I don't see anything else that we can simplify here. So this is this term multiplied by A. Now let's look at this whole term multiplied by this. So this will be, if you multiply this with this, so you will get A inverse U V transpose. Sorry?
A plus.
You're right. Yes, this is I plus. Yeah. So if I'm multiplying, I'm post multiplying, so this will be A inverse U V transpose, and then minus 1 by 1 plus V transpose A inverse U, and then this whole thing multiplied by this, that will be A inverse V transpose inverse yeah. Now we'll do the same thing that we did here, right? So you multiply this here, so we'll get have. We call that the denominator. What will happen if you multiply this with this? What is the first term you get? It's this matrix multiplied by 1, so it will just be this matrix. Go here. You're post multiplying. So this will be plus A inverse U V transpose multiplied by V transpose A inverse U. Okay. Is this minus, that is minus sign, and then this whole thing. Okay. Is it clear so far? Okay. Now, before we proceed, right, let's look at this. See, if you look at this whole expression, maybe it's confusing, but we know that this expression is a scalar. Okay? Because this was a scalar. That means I can move this to the front. Whether I write A times 5 or 5 times A, it gives me the same matrix. That means I can move it here, right? I get A inverse E transpose plus E transpose A inverse U A inverse E transpose. Okay. Now, so we've got this multiplied by this multiplied by this. So if we just add these two, hopefully it will come out to be I. Then we terms that cancel out, and then we'll get I. We don't have to worry the denominator because it's common for now. So let's not worry about that. And let's see if we can just do stuff from here. Okay. So we are adding these two numerators, right? We have a minus A inverse U V transpose. We have a plus this one, so this is gone. Sorry, yeah. AI. Yes. Yes, okay. The only reason I'm keeping it here because I didn't want to look like I'm adding a matrix to a scalar. The reason I'm keeping the I is because I'm saying this is you're adding two matrices. Otherwise, it look like I'm adding 1 0 0 1 plus 5. That does not make any sense. What makes sense is this. That is the reason I'm keeping. Otherwise, you're right. But here, this multiplied by I is in fact some scalar multiplied by I. It's not just a scalar. Yeah. So this is gone. Yes, that's right. Yeah. What else can we do?
If there is a matrix instead of a scalar,
You can remove the I. See, if I multiply this scalar by I, what I really have is 1 plus, I'll call this some alpha. This is equivalent to I plus alpha I. That is why I'm keeping the I here. Yeah. Is there anything else that cancels out? We can't see it, but let's see. Okay. This is out, so we have this. Do we see terms like this here? We do see this here. Sorry. Yes, that's right. So here, right, we can let's see if we can do something else. This thing is repeated here. Okay. But we know V transpose A inverse U is a scalar. Okay. Look at this term. V transpose A inverse U. This is a scalar. That means if I group these two together, this simply comes out as a, and that means I can move this whole thing to the front, right? Is that clear? Because that forms the scalar. So the reason again I decided to do the problem here is because whenever you're dealing with lots of matrices and vectors like this, you need to look for stuff like this to simplify the expression. So for now I'll keep this. So A inverse U V transpose plus V transpose A inverse U A inverse U V transpose. Now, if you take this whole thing outside, then you get minus V transpose A inverse U. If you take this out, all you're left with is A inverse U V transpose. And divided by the denominator. Okay. Now, this is plus scalar A inverse UV transpose. That's negative, so these two are gone. So effectively by multiplying this with this, all you're left with is this term divided by the denominator. And this term gets cancelled by this. And all you're left with is this. And that is nothing but I times 1 plus V transpose A inverse U. And what is the denominator? So it's 1 plus V transpose A inverse U. Store out, so you're left with I. You do now you can do a similar thing. You put this here and then verify that this whole thing simplifies to that. Okay. All right. So with that we'll stop, and then we'll continue on Monday with the new module. Okay. All right. Thank you.